Next, we have a talk by Stephen Covey on the subject of asteroid capture and space solar power. Please.
Thank you. I'm going. This presentation focuses on a specific technical approach that allows us to capture an asteroid into Earth orbit, and then we can use its resources to build solar power satellites and other things. Yesterday's talk was more detail about how you actually capture an asteroid using slingshots around the Earth and the Moon, because we can do it with fairly small amounts of delta V, which is the really enabling trick. The project plan I talk about will go through the details of things we need for the capture, and also a first draft of what we would need to send up mining, smelting, manufacturing, other kind of components for that. We throw in a number of launches required, let's see, timeline, cost, and I throw in some profit figures. Next slide. So why capture an asteroid? The main reason is to gain convenient access to its resources. Even a relatively resource-poor, low iron, low metal asteroid such as 9942 Apophis contains 27 million tons of resources, about 20% of which is iron, most of which is oxygen, and it still has large quantities of everything else that we'd need, except possibly nitrogen. But it even has significant quantities we expect it has significant quantities of water and carbon as well. Now, one problem with capturing this particular asteroid is that since we're using an existing slingshot to get our results, we are tied into a specific date. The asteroid is going to make a close approach to the Earth inside of geosynchronous orbit on April 13th of 2029. So we have to put our project around that. We can't change that. Many of these dates are driven by these orbital dynamics, and there won't be a choice. I'm going to assume pricing and capabilities of the SpaceX Falcon Heavy that's been announced, but of course not built or let alone flown. I don't. We'll need to adjust the numbers for inflation, for cost of money. I put in some fairly high worker launch costs initially because I think people will have to do this, not robots. But I assume that the prices will be dropping over time as we send more and larger missiles, rockets into space with more people on board. I don't include worker salaries. I figure if it costs $1 million or $30 million to get a worker up there, his salary is inconsequential. I don't include most R&D costs, and I'll get into that in a little bit. Direct R&D costs, yes. And for income, I'm only going to include sales of energy from solar power satellites. I mean, my profit figures will not include things like tourism, sales and rentals of retail space, propellants, sales of propellants, product placement, tie-ins, naming rights, or anything else. Just 3 cents per kilowatt hour wholesale electric. That's a low price, but should be doable. Next slide. Yesterday's talk really went into detail about how to capture an asteroid, but the main thing here is we'll be launching the project. The first launches are actually in 2027. We have to do our orbit intercept launch has to occur in October of 2027. Then we will be thrusting for 5 months to match orbits and dock with Apophis. That takes about 3 kilometers per second of delta V. And then we'll need to push very hard on Apophis at about 6 billionths of a G. Works out to be 1 centimeter per second per month of acceleration. To do that, we only need an average of 200 newtons of thrust, which is something achievable with ion thrusters, Vasimar, magnetoplasma dynamic, things like that. The big slingshot is going to be the one around the Earth on April 13th, Friday the 13th of 2029. We can't change that. All we're really doing is a little bit of a small change. It's we are delaying Apophyse's arrival at the intersection of Earth's orbit by 200 seconds. That's all we're doing, and that little result, this 10 centimeter per second delta V, makes that much difference over 6 months, and that will result in a 1.5 kilometer per second change in Apophyse's new orbit, and that's the real enabling feature here. The total, instantly, it's only going to change it so that it comes back around and intercepts a year later in April of 2030. And that one will be a close approach slingshot around the moon, which is the one that actually drops it into Earth orbit. So we're talking about dropping the Apophis into Earth orbit in mid-April of 2030. It's a 32 month mission total for deep space. So that's one of the things we have to address. Next. We need a tug ship to do this. It has to be, I figure it has to be assembled in low Earth orbit from modular components. The core is, of course, the crew quarters, life support, tools needed to grapple an asteroid. It'll need, well, it needs at least 10 megawatts of solar panels, or a nice nuclear reactor and some other things. But I budgeted 100 tons of solar panels and structure. To generate basically 12 megawatts. That should be enough to do a 200 by 200 meter solar power array. We'll need about 100 tons of fuel and enough thrusters to do 200 newtons of thrust. Actually, we need 400 newtons of thrust. Because we'll only be operating the thrusters half the time, but because Apophis is rotating. Now the total of that is 250 tons. I figure that's 5 Falcon Heavy launches, $600 million rough cost, another $1.5 billion for the components. And this cost is lower than a lot of large space-based projects because of extensive use of modular components assembled by people in orbit, because people are good at solving problems and getting things to work when they didn't work right the first time. And we will have some tight timelines to follow here. After it's assembled, we'll launch a mission crew at the last minute, and because they're already going to be spending a lot of time in space, 32 months, I figure. And then basically the total capture cost, the cost of this part of the mission is $3.8 billion in my estimate. That doesn't include upfront research, but it does include what I think will be the components we'll need to affect the mission. Next slide. Okay, to launch once we capture the asteroid, we need to exploit it. Mining and manufacturing is a big unknown. We don't yet know how to do mining and smelting and refining and manufacturing in microgravity conditions. Plus, we're going to need to save everything. We're going to need to recycle reagents. If we use hydrogen for smelting, reducing agents, we're going to have to recycle that. We can't just blow it all off like we do in modern steel production and stuff today on the Earth. So it's a total different paradigm. But I've budgeted a bunch of components so we can do this, I hope. Let's see. And I also figure we're launching these things in low Earth orbit, and the tug ship itself will be refueled, and we'll ferry the tools up into the orbit where the asteroid is, which is actually a high Earth orbit. We need a solar power generator. Now, I budgeted 6 megawatts of power just for the factories. We'll need mining facility, ore movers, grinder separators. I've budgeted a couple of launches that's at 50 tons each and $400 million. We'll need solar smelters, gas collection refining, metal purification. I've budgeted 5 launches and $1 billion for that. Steel production, another 5 launches, another $1 billion. A rolling mill, we need to produce girders and sheets and rods and things like that. Another 3 launches, 600 mil. Finished metal product plant. We need to turn these things into nuts and bolts and rivets and connectors and pipes and tanks and toilets, whatever. We need to build everything in space, and it takes a lot of infrastructure to do that. That's another couple of launches, another $400 million. We'll also need a silicon refinery and facilities to manufacture solar power panels. I've budgeted only 3 launches and $600 million for that. Let's see, we even have to process slag. So the slag that's up there, we're going to be turning it into shielding for habitats. We're going to be turning it into rock wool for insulation. Anyway, that's another couple $100 million worth of processing for slag. Total estimate for those things, $4.4 billion, 22 launches, and it spans just that narrow window of 2030 to 2031. Next slide. The workforce and construction shack launches could begin in 2030. I figure we're initially going to start off with 36 workers to get started. It's just enough to prove the feasibility of mining and refining and manufacturing in space, but is way inadequate to achieve any significant levels of production. For that, we have to start ramping up. By the time we ramp up to 500 workers, end of 2031, our steel production rate should be about 100 tons a day of steel production. That's not actually very much. Think of it as what, 12, 13 cubic meters of iron, of steel. Let's see. But that's enough to allow us to construct a habitat pressure shell by the end of the year, so that we could actually pressurize it with oxygen and start living inside with gravity, with artificial gravity. Okay. The next year, doubling the workforce in the next year allows us to get our production of steel up to 200 tons a day. That's enough to actually build a solar power satellite. So we will be trying to build a solar power satellite, have our first one completed by the end of 2032. Let's see, and we keep doubling it so we can build more and more solar power satellites each year, but I top it out at really 7,500 workers because the habitat I propose building has a capacity of 8,000 workers. It's the smallest reasonable habitat. I'll go into that in a little bit. For proper shielding and things. Now, by the end of, key thing there, by the end of 2035, we should have our first permanent habitat with an 8,000 person worker capacity completed and 15 solar power satellites. Now, next slide. A little bit of overview on constructing a 5 gigawatt power satellite. That's what I'm talking about doing. 5 gigawatts requires a lot of solar panels, a lot of steel structures. I've used the fairly high, in some terms, mass calculation, 25,000 tons, which is 5,000 tons a gigawatt. It's possible to be done for less, but hey, if these resources are in space, we don't really need to worry that much about total mass. They're already there. Remember, there's a lot of available mass in the asteroid. However, we do want it to be as efficient as possible, because while the mass isn't really that critical, the size of the solar panel array is, because of the labor required to put the thing together. So more efficient ones mean smaller arrays. And there's also a possibility of improving these numbers by using thin film mirrors and concentrating sunlight to get higher energy from a smaller array. Next slide. Once we build it, it's been built up somewhere near lunar orbit where the asteroid is. We have to deploy it down into geosynchronous orbit. And main thing is that takes a lot of fuel. These things weigh 25,000 tons. And we need 2 roughly 2 kilometers per second of delta V to move it into geosync from up there. And even using 5,000 ISP ion thrusters, we're talking about 1,000 tons of fuel is needed. Luckily, 1,000 tons of fuel is a small amount compared to the oxygen produced by the smelting of all that iron. The iron we produce will be 5,000 to 10,000 tons for the iron to produce that one solar power satellite. That means we'll be using a small, if we use oxygen as our thruster fuel, we'll be using a small fraction of that to achieve our orbit change. We also have a lot of power available, so we can move it as fast as we want because we'll have gigawatts of power. If we want to put up enough thrusters, to get a higher flow rate, we can do it quickly. On the other hand, I've budgeted, in terms of my timing for my profit stuff, I've budgeted a 4-month period for how long it takes to move it down into GEO. Once we're in GEO, we need to install components that come from Earth, which primarily, I think, is the microwave transmitter electronics. Everything that's heavy, we're going to build up there. But the things that are really high-tech, we have to build on Earth and launch. I budgeted a couple of $100 million for each solar power satellite to build and launch these microwave transmitters. Of course, each solar power satellite will require a matching ground receiving station, you know, the usual 10-kilometer rectenum, plus power conversion, distribution. And I haven't really heard good numbers for costs, so I've budgeted $1 billion roughly, but I figure it's not part of my budget because the receiving utility will build that so that they can receive electric power. So it's not part of my budget. Okay, a little bit about habitats. I figured the workers, if we're putting 7,000 or 8,000 workers in space, they need a place to stay that's got all of their living requirements provided. Gravity, oxygen, water, food, you name it. Radiation shielding. And I've, using the design, the Kalpana 1 habitat design, Al Globus and others have written an excellent paper, the Kalpana 1 Orbital Space Settlement Revised. And I modified their designs a little bit. For one thing, I made it smaller, only 1 G for rotating at 3 RPM. I've assumed several differences, like no natural sunlight, but using high efficiency LEDs to get the power consumption down, because it's a thermos, and the capacity of it is limited by how much heat can be radiated off of its surface. Still, that means that a 100-meter radius, 130-meter wide cylinder spinning at 3 RPM will support a little over 8,000 people with 10 tons per square meter of shielding around the entire shell. Turns out that that's not that hard to do. The standard engineering calculations, it takes less than an inch thick steel shell to support 10 tons of slag on the outer shell and the atmospheric pressure on the inside. And that's using average strength, easily weldable steel. None of this high strength stuff that when you weld it, it loses all of its strength. I tried to go conservative there. Now once it's built, we can easily spin it up, pressurize it, and start living inside as we bring in shielding, because the shielding is going to take a lot of time to generate that much slag. It's going to take, by the time it takes all the shielding, all the slag produced by building 12 solar power satellites to provide enough shielding to shield the whole thing. So it'll be shielded a little at a time until it's done. I've also budgeted 126,000 tons of interior steel structures along the outer walls, along the rim for living areas, a core structure. I would like to point out that the total tonnage here of the 28,000 ton shell and the 126,000 ton of the interior structures is significantly less tonnage than an Oasis-class cruise ship, which masses 225,000 tons of steel, and it also carries about 8,000 passengers. This thing's much more spacious. So, okay. We also need power. 6 kilowatts per person is what I think we need for growing plants and normal usage. That's 50 megawatts for the whole thing. All the extra power for a smelter and stuff like that, I view as outside. If outside factories have their own power separately from this. So it's not part of my budget for the habitat. Now it actually takes a lot of fuel to spin this thing up, because it starts off, it's not spinning. And it takes about 1,150 tons of fuel, again, just to spin this up to 1 G. But luckily, 3 RPM, so it's got generating 1 G on the outer rim. The good thing is that the empty shell will spin up very quickly, and we need most of that energy to keep it spinning as we slowly bring 1 million tons of slag in for shielding and put it along the outer rim. This habitat features a lot of things. 5.5 million square feet of agricultural space, 2.5 million of residential, which is equivalent to 300 square feet per person roughly, which is the same as the rooms over in the hotel here for a couple. Our hotel rooms are 600 square feet. Actually, they're a little bit less. So that's how much space we're talking about. So if you think you could live in that, that will work. Okay, we'll speed up a little bit. After we've gotten this first completion done, the 15 solar power satellites and a habitat, we actually have the capacity to build more. We've also used less than 10% of Apophis, and we could replicate this actually more than 9 more times. We could build totally of 150 solar power satellites, and that's supposed to be 150, not the 8-year plan. The total one will be 150. Now, global powered electric demand is 400. Would take 400 solar power satellites to fill, 5 gigawatts each. Let's see. And of course, I really think we need to build more and larger habitats. Maybe near geosynchronous orbit to provide a better location to build and maintain satellites and solar power satellites. We might want to put them in L5. We might want to put them in transitional orbits like that help us get to L5 or something. There's some platforms that are fairly ideal for launching interplanetary missions, including to Mars. And speaking of Mars, what better way is there to travel than one of these things with 8,000 of your closest friends? And if we get to Deimos, for example, which takes 175,000 tons of fuel, which we actually will have, it's large enough to build 50,000. It's 50,000 times as big as Apophis. So it will build a lot of habitats, enough to support the entire Earth's population. Almost 6 billion, I figure. Phobos is 7 or 8 times larger. So. Okay, return on investment a little bit. I'm assuming 1.3 billion a year of cash flow once the SPS 5 gigawatts is operational. That means that by 2036 we'll reach break even after a peak outlay of just under $25 billion. And if we just stop there, by 2037 we'll make $19.5 billion a year of revenue with no additional cost. Or we could take a different approach. Instead of selling power, we could sell satellites. If you sell a solar power satellite, 5 gigawatts for $5 billion, that would be dirt cheap as far as a power company is concerned. You actually make money in 2034, and by the time you're building 8 power satellites a year, your revenue is $40 billion a year. So it's pretty profitable. Even that $25 billion is comparable to what my own power company down in Florida is building on a nuclear station, a nuclear power plant. The per gigawatt price is about the same, and and of course no one here would object to solar power satellites in their backyard arrays versus nuclear plants. Okay, next. We do need to do a lot of research and development. A lot of areas require it. And it's an unreal oversimplification, but I've ignored the fundamental R&D costs for this project, although they're large and unknown, because I think that NASA, various governments, universities as part of federally funded research and things should undertake much of the fundamental research. Now, all the directed research for specifically how to build a device that is going to be sold, that should be handled by the company that's doing it. Variety of characteristics there. Okay, my conclusion, last slide. We can do this, we can do it, we can actually make money by 2036, starting to spend it in a big way in 2027. So it's almost a 10-year time frame. And reality, I've been accused of being an optimist. It's likely to take longer than this project plan. It's because there will be unforeseen setbacks. I've ignored the cost of money. I've ignored the cost of bringing all these workers back to Earth, assuming they'd want to return. But even if it takes another year or two before break even if the costs run 20% or 100% higher, even if you factor in the upfront R&D costs, and even if you add a generous salary for every in-space worker and free room and board, it's still going to be wildly profitable. Solar power makes a lot of money in space. And I like that at the end of the extended project, we've not only accomplished a great deal with generating all these solar power satellites and making lots of money, but also Apophis at that point is just a memory. It's gone. It's no longer a threat to anything because it's been turned into infrastructure. Now, last point, is there an entrepreneur listening that likes the sound of a $200 billion per year free cash flow for a $25 or $30 billion investment? And with a little bonus of earning a permanent place in the history books for bootstrapping humanity's move into the solar system? That's all. Thank you.